Hi, this is Marcin and Andre again. In this video we'll show you how to manage a grid engine service with the Service Domain Manager 1.0 update 3. We'll demonstrate the installation with the system that we prepared in the previous video, the installation of the SDM. Let's recapture first what already is installed. We work on a set of 6 hosts, node 0 to node 5. On the first host, node 0, there is a grid engine cluster pre-installed under /opt/sg directory. The cluster solely consists of a QMaster. It has no compute host resource assigned. Then there is a basic SDM system installed under /opt/sdm. It is named MySDM. The SDM master host is running on node 0. Node 1 to node 5 are installed as managed resources. They are currently assigned to the only service of the system, the SPELPUR service. The grid engine cluster and the SDM system are installed as separate systems. To let the SDM manage the cluster, the two systems need to be somehow connected. The connection can be established with the grid engine service adapter. The adapter allows SDM to manage the grid engine cluster as a scalable service. The grid engine service adapter installation requires some parameters of the cluster configuration. To identify the cluster, the name of the cluster and the cell are required. Here the cluster is named P6444, the cell default. Then the cluster's admin user and its credentials will be needed. Here the admin user is root and his keystore is located in /var/sgca/port 6444/default/userkeys/root/keystore. Finally, the set of ports for the QMaster, the execDs, and the JMX communication will be required to configure the adapter. Here the QMaster port is 6444, the port for the execDs is 6445, and the JMX port is 6446. This is the complete set of parameters required to proceed with the installation. To install the grid engine service adapter, we log in on node 0 as the root user. Let's check that the grid engine cluster is running. We source the cluster configuration. As you can see, the cluster is currently running but empty. Let's continue with the pre-installed SDM system. We switch to the distribution directory and check the installation. Our system MySDM is installed. The show resource command shows the complete set of 5 host resources. All resources are currently located in the SPELPUR. As we can see with show service, no other service is currently managed. We will now add a grid engine service adapter with the name GAdapter to the local host node 0. As we want to start the adapter directly, we add the -start option. Executing this command will automatically open a configuration file in the system editor. This XML-based configuration offers a lot of parameters and options to adjust the adapter to various use cases. For now, we want to establish the connection to the cluster. Thus we will only edit the connection section and use the pre-configured defaults for the remaining parts. First, we will provide the installation directory and the names for the cluster and the cell. Then we will specify the admin user and the location of his key store. By default, no password is required to access it. Finally, we will enter the set of ports for the communication. Let's save the configuration and test if the connection to the cluster works. The add G service command reported that the G adapter has been added. Let's check if it has been started too. The show service command reports that the G adapter service is running. SDM was able to connect to the configured cluster. As a next step, the scaling behavior of Grid Engine service has to be defined. This is done with the configuration of service level objectives, SLOs. SLOs define the resource request behavior of the services. The current SLO configuration consists of a fixed usage SLO for the Grid Engine adapter and a permanent request SLO for the spare pool. This means that the spare pool permanently requests resources with the lowest urgency of 1. The fixed usage SLO will not request any resources for the Grid Engine service. However, if a resource is explicitly added, it will get the usage of 50 assigned. With this setup, no dynamic resource relocation will take place. We will now replace the fixed usage SLO with a max pending jobs SLO in order to get a scalable cluster that can dynamically adapt to different workload profiles. The max pending job SLO will be configured to request resources with the urgency of 10 for every job queuing up in the cluster. To exchange the SLOs, we will edit the Grid Engine service adapter configuration again. In the SLO section, we will replace the predefined fixed usage SLO with a max pending job SLO. I will do just copy and paste here. This SLO assumes that a host can only handle a single job at a time. If there is at least one job queuing up, the SLO generates a request for the corresponding amount of resources with the urgency of 10. Let's save the configuration and apply it. The show SLO command confirms that there is now a max pending job SLO defined for the grid engine adapter. That's it. These were the necessary steps to add scalability to the grid engine cluster. Let's submit some jobs to see the cluster scalability in action. We will submit 2 dummy jobs with a runtime of 1 minute into the cluster. The cluster does not have any compute hosts and therefore no job queue to submit to. That's the reason for the warning messages. As expected, both jobs are waiting in the pending queue. The 2 pending jobs have been detected by the max pending job SLO. It now requests 2 host resources. The show resource command reveals that the requested resources have already been moved to the grid engine service. They get their execds installed so they can be added to the cluster. The installation has been completed. The 2 host resources are now assigned to the grid engine service. The QHost command shows that the 2 resources are now known in the cluster. Furthermore, qstat reveals that the 2 pending jobs are already scheduled and started on the new hosts. Jobs are still there. Still. Now that they are finished, the 2 compute hosts started to run idle and the max pending job SLO will no longer assign a usage. As the usage drops to 0, the spurpool can request the idle resources back with the permanent request SLO. That just happened, the cluster is now empty. The show resource command confirms that the 2 resources are just about to move back to the spurpool. And here they are. Let's summarize what happened in the SDM system. At the beginning, the cluster was empty and no job was queued in the pending queue. All resources were located in spurpool service. We submitted 2 jobs that queued up in the pending queue, and the max pending job SLO requested 2 host resources with the urgency of 10. The requested resources were moved from the spurpool into the grid engine service and added to the cluster. The pending jobs were scheduled on the hosts and the pending queue became empty. After some time, the jobs were finished, so their usage dropped from 10 to 0. As the usage was not lower than 1, the resources could be re-requested by the permanent request SLO of the spurpool. This is the basic SDM configuration to turn a grid engine cluster with a static set of resources into a highly scalable one. As a next step, the SDM system could be extended with additional grid engine adapters to manage a set of independent clusters. We call this elastic multi-clustering, as resources can then be shared between clusters depending on their workload. That's it for now. If you want to see more of the system in action, take a look at our Cloud Service Adapter video. Finally, you may want to check the Grid Engine and SDM product pages at www.sun.com/software/sge and the online documentation at wikis.sun.com/display/gridengine. Thank you for watching this video.